You ever see a small difference between two things and just wonder? Is that a real discovery or is it just some random fluke? How do scientists actually figure that out? Well, let's dive into the powerful tool they use to get to the bottom of it.
Okay, picture this. Let's say we're testing two brand new painkillers. We give drug A to one group of people and drug B to another. After a while, we check in on their pain relief and, well, one group says they're feeling a little bit better. So, is that drug the winner? I mean, could we run the exact same test tomorrow and get the complete opposite result just because of random chance? So, now you've got your data. Group A, on average, reports their pain relief as a 7 out of 10. Group B, they're at a 7.5. Now, on the surface, it looks like B is better, right? But is that tiny half-point difference really big enough to declare a winner? Is it a real, meaningful effect, or is it just statistical noise?
And this is the fundamental question, isn't it? It's one thing to see a difference in a small sample of people we tested, but how can we be confident that this same difference exists for everyone, out in the real world? That's the dilemma we've got to solve.
And to solve it, we have this brilliant statistical tool that was designed for exactly this purpose. It's called the t-test. And you can think of it as our guide for separating a true, meaningful signal from all that random noise.
So what is it? Well, to put it simply, the t-test is a statistical test that looks at the average results, the means, from two groups. And it tells us whether the difference between them is big enough to be considered statistically significant.
In other words, it helps us answer our big painkiller question. Is drug B genuinely better, or did we just get kind of lucky with the specific people we happened to test that day? The t-test is what gives us the power to make that call with some real confidence.
Now, what's really interesting here is that not all comparisons are created equal. There are actually 3 different types of t-tests, and each one is designed to answer a slightly different kind of question. So let's break them down.
All right, let's start with question number 1. Imagine a company claims its fancy chocolate bars weigh 50 grams each. So you go out, you buy a whole bunch of them, you weigh them all, and you find out the average is only 48 grams. So are you being ripped off, or is that difference just a normal random variation?
To answer that question, you'd use what's called a one-sample t-test. It's designed for this exact scenario. You're comparing the average of your single sample, all those chocolate bars you bought, against a known established number, which is the 50 grams the company is claiming.
Yeah, the setup is really simple. The company's claim is 50 grams. Your sample averages 48 grams. The one-sample t-test is what determines if that 2-gram difference is actually a big deal or if it's just, normal random variation you'd expect to see.
Okay, so let's circle back to our original problem with the painkillers. Here, we're not comparing our drug to some known number, right? We're comparing 2 new drugs against each other. We've got 2 separate groups getting 2 different treatments.
This situation calls for something different. An independent samples t-test, and it's called independent for a really simple reason. The people in Group A have absolutely no connection to the people in Group B. They are 2 completely separate, unrelated groups of people.
So the crucial part is all in the setup. We take, say, 60 people, and we just randomly divide them in half. One group gets drug A, the other gets drug B. The test then compares the average pain relief between these 2 independent groups to see if one drug truly outperforms the other one.
Okay, on to our third and final question. Let's say we want to test a new diet program. How would we do that? I mean, we probably wouldn't compare dieters to non-dieters. What we really want to know is if the same people actually changed over time.
For a classic before and after scenario like this one, we use a paired samples t-test, and it's called paired because every single data point in the before group is directly linked or paired with a data point in the after group. Why? Because it's the very same person.
So here's how it works. You take 30 volunteers and you weigh them. Boom, that's your before data. Then they all go and do the diet program. Afterwards, you weigh the exact same 30 people again. That's your after data. The test then just checks if the average change in weight is big enough to matter.
Okay, so let's put these 2 side by side just to make it crystal clear. Independent samples, that's when you have totally different people in each group, just like our painkiller trial. Paired samples, that's when you have the same people measured twice, like in our diet study. It's the question you're asking that determines which tests you need to use.
Okay, so we know what these tests do, but how do they actually think? What's the logic here? Well, the whole thing starts with a really simple, kind of skeptical assumption.
This assumption is called the null hypothesis, and in plain English, it just means the test starts by assuming there is no real difference. It assumes that chocolate bars really are 50 grams on average, that both painkillers are basically the same, and that the diet, well, it does absolutely nothing. The entire job of the test is to see if we have enough evidence to prove that skeptical assumption wrong.
And this brings us right to the core mission of the t-test. It's all about finding that threshold, that tipping point. At what point is a difference big enough that we can finally confidently say, you know what? This isn't just chance. Something real is happening here.
So how do we make that final call? How does the t-test give us that definitive yes or no on whether our result is significant? Well, it all comes down to one magic number.
And that number is 0.05. In the world of statistics, this is the most common significance level. It's also called the p-value threshold. And you can just think of it as the line in the sand.
And here is the simple three-step rule. First, the t-test crunches the numbers and calculates a value for you, called the p-value. Second, you take that p-value and compare it to our line in the sand, 0.05. And third, this is the big one, if your p-value is less than 0.05, you've done it. You can officially reject that skeptical null hypothesis and declare that your result is statistically significant. The difference is real.
So, the next time you read a news headline or you see an ad that claims a significant result, doesn't matter if it's about a new drug, a diet, or anything else, you'll know exactly what's going on behind the scenes. You can now ask the real question. Okay, but was the p-value less than 0.05? And you'll actually understand the powerful tool they used to find that out.